Okay, so today's class is a bit leftover pieces of what we have skipped and so on in the whole range of chapters from 1 up to 5. So we will fill in all the holes and then move on with chapter 6 next time. So the first thing we're going to do is 4.5, where we finally get the last piece of the puzzle, why LQ is the dual of LP, P less than infinity. And then we're going to talk about completeness and regularity of measures. Basically, this is section 1.5, which we never properly did. We're done 1.1 to 1.4 and 1.6, which was needed for Completeness theory, remember? But not 1.5, completeness and regularity. So that's the lineup for today. Let's finish this topic about duality, right? So we had already established most of it. In the end of section 3, right? So we know that we want to prove that the LP dual is equal to LQ. And we had established that the LQ is a subset in the following way, that if you take a function g in LQ and you send it into the linear function of TG, this is in the dual space, so this is an isometry sending g into TG, where TG is a linear function, so you can apply it to an f in LP, and then you just integrate f against g. So this is where we were, and then we had that TG, the norm as a linear functional, was equal to the norm of g in LQ, right? So I could put a Q here. Maybe here I could also write something, but let's not do that. So this is norm as linear functional. So we found this identity. And the way to do that, I mean, Hölder's inequality gives you that the norm is less than or equal to this. And to see that you actually get equality, was this, we need to find a function f, so that here we get really this value. And then the key idea was to make this clever choice of taking f equal to g. Basically, well, okay, in the positive case, we took g to the power of q minus 1. It turns out that this is now in LP, and yada yada. In the general case, you have to put some sign here, right? So then you engineer it so that when you do TG of f, the modulus here you won't need. Well, okay. So in the definition of the operator norm, we're interested in this, right? And then with this choice, or with this sign, you fiddle so that you always get a positive number here, or if this is complex value, you just make sure that this guy has the opposite angle all the time, but this modulus. Yeah, so let's put it like this. You make f so that it satisfies this, and then you make sure that the angle is such that you always, in this product, get a positive number or non-negative. Okay, so then here you get integral modulus g to the power q du mu, and down here you get g to the power q minus 1 in P norm. But it turns out that this can also be computed in terms of the Q norm, actually, because there's this like magic identities for the P's and the Q's. So at the end of the day, you get that here out comes just this. So up here, you get the Q norm to the power of Q, and then dividing by this, you actually get rid of that power. Very clever. So we can see this as two sets, right? So here's LQ, and here's LP star, and then this duality sends this into potentially a subset here, right? So it could be the case that this is actually much smaller and it's just sent to a subset here, so it's not certain that we get all the linear functionals by this type of functional. So how can we prove that? And actually I already outlined when we spoke about this last time, how to do the proof. So first you assume that mu is finite. The duality is only the duality theory is only true in the sigma finite case. So mu is finite. Why do we need that? Because well, we need it in various places, but we're gonna, if we have such a formula, then the measure mu, well, okay, then G times d nu is a measure which we can call nu. And if I let f be a characteristic function, I'm just getting that measure, right? So if nu, so d nu is equal to G times d nu, right? I mean, I don't have these guys yet. I have to construct them, but if you believe they exist, then it makes sense, or to expect that they arise from this construction, right? Where here's the characteristic function of A, and this is a function in LP, so I can apply my function to it, and then I should get out what I want, the integral of just G times the mu. So that's a measure. Okay, so where do we need that mu is finite? Well, for one thing, to prove that this is a measure. Yeah, so I think I already outlined those computations, but they are in 4.5 otherwise. So basically, when you check that something is a measure, that is infinite summation formula. And that boils down to basically you need to use dominated convergence theory, and then you need a finite measure, because then characteristic functions, they're bounded by 1, so the function constantly 1 can be your dominating guy if you have a finite measure. Otherwise, constant functions are not integrable for infinite measures, right? And even this definition here would not make sense if you allow infinite. If you have an infinite measure mu, then you could get infinity here. So that some characteristic functions would then not be possible to stick in there. So this is a very crucial assumption. I'm going to do the proof or explain the key idea in the finite setting, and then you can extend it to the sigma finite case. That's just a boring detail. So it's in the book or an exercise, what you want. Okay, so anyways, we define a set function like this, and then we prove, as I said, with dominated convergence theory, that it is indeed a measure. Here we got stuck last time. And what was it we didn't have? We didn't have the concept of absolute continuity. Now, clearly, if I stick in a set which has mu measure 0, then the LP norm of that characteristic function is 0. And therefore, I get 0 here, right? Linear function applied to 0 gives you 0. Meaning that nu is absolutely continuous with respect to mu. So this is a measure, and mu is absolutely continuous with respect to mu. And then the Radon-Nikodym theory tells us immediately that there exists a function g such that, well, basically that holds. Let me write it again. And now we're almost done, right? But not really. So what we have now is nu, well, okay, so we have Tg of a characteristic function of A. That's the same as integrating against g times mu, and g is now an L1 function. Now, from here, it is very easy to see that as long as this is, I guess, a bounded function, then at least, I mean, you do an approximation argument and you get this. So this step is not difficult. But so, all right, so now we have this, what we want. The problem is that we don't know that G is in LQ. We know it's in L1, but LQ is a smaller space. when mu is a finite measure. Okay, so how do we do that? And here is a very clever trick they do. So, because now armed with this, we get a function g. So we can check where it's big. You know, all bounded functions, they're LQ if you're a finite measure. So we have to avoid the set where g is big, okay? But g, now it exists, right? So it tells us where is the places we have to avoid, right? So what we're going to do is, for all n, you look at En to be the set of x such that g of x is bigger than n. All right? And now you define this measure Vn of A, and now we repeat the whole thing. It's just that here I'm going to do Tg, characteristic function of En intersect with A, or easier actually to just multiply them. Okay, so that's the same thing. Right? Now, you go through the whole argument again. So this gives you a function which we can call Gn. But of course, G and Gn is going to be the same almost everywhere on the set En, right? In the sets En, they grow. So you get a sequence of functions like this. So G1, G2, dot, 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 such that G restricted to En is equal to Gn almost everywhere. So that's a mu almost everywhere. Now, here's where it gets nice. Okay, so you have basically you have convergence almost everywhere. The sequence Gn converges to G almost everywhere. And now is where it gets really clever. So we have this formula now with Gn here. And then I have to put a characteristic function of my En there. We have this formula. What can I do with this? I can actually, so here, I pick my f to be, I'll just do the same thing with my Gn, right? And I know this is bounded by the norm of G as a functional, so Tg as a functional. So what we get, I have to get a new here, is that Tgn is less than or equal to Tg is less than or equal to, now you stick in your G, this computation here, you do it, and then you see that En in the Q norm is bounded by this, which is bounded by that. So we get a sequence of functions that converge almost everywhere to G, and they are uniformly bounded in the LQ spaces. Well, then they converge. That's another just dominant convergence theory. Then they actually, you know, the limit point is also then LQ, and the norm of the limit point is less than or equal to that. So then you have Tg bigger than or equal to G in the Q norms. Now we know that the function G is actually LQ, and that's it. Then we see that this space here, the LQ, is actually equally big as this one. So figuratively, this circle and that circle, that's the same size. Very nice. Right, so read the details yourselves. And that's the end of chapter 4. Okay, so switching now to completeness and regularity. So remember that we had this, so the Brev sigma algebra on R, or RD for that matter, was a subset of, but not equal to M lambda star d-dimensional, okay? But we never got a real clear picture of who these sets are, right? We were always saying like, yeah, this even the Borel sigma algebra is so big, there's no constructive way of reaching to these sets. And then like how are these two related? Or is there anything in between here? It's kind of incomplete, the story, right? So today we will complete the story, starting with completeness. So if you have, I think I mentioned this previous in the course, but if you have that A is less than or equal to some set E, which in turn is less than or equal to B, and if mu of A is equal to mu of B, if this implies that E is in, whatever sigma algebra you're working on, then that sigma algebra is said to be complete. And actually, this is not a definition, this is a consequence. It's very easy to see. So this, if you take this as the definition, then it's equivalent with the following statement that if E is less than or equal to B, and mu of B is equal to 0, then E is in A, right? That's the technical definition of completeness. But if you have that, then you just play here with, so E set minus A will be a set of measure 0. It's in the sigma algebra, and then you just take a union with A, and you get this statement here. So these two are equivalent. Right, and we saw that Lebesgue measure has this property. So in particular, Lebesgue measure is complete. Let's write LD for d-dimensional Lebesgue measure is complete. Well, it is complete on m lambda star d, right? This is a complete sigma algebra, and then this one cannot be a complete one, because otherwise they would be the same. Now, next thing, if you have a sigma algebra which is not complete, yeah, then you are in the situation that there are some sets here stuck in between measurable sets, but they are not themselves measurable. Then, of course, you can define the sigma algebra of all sets E with that property, right? So if yeah, so this is something which is easy to check. If A is not complete, then you just take the set of all sets E locked in between sets of the same measure like this, and you see that that's a sigma algebra. It's not a difficult proof. I think it's 151. Yeah, no, there's something going on there, but not too much. But anyway, let's keep our head a bit about the vocabulary here and not start in details. So this is a true statement, and then of course you can extend your measure mu to these new sets E, by just defining the measure to be either this or this, I mean, this common value here, right? So right, so if we define that, then mu dash, whatever it's called, the completion of mu, it's called, it becomes a measure on the completion sigma algebra. So this is just proposition 151. You can look at the details there yourself. So is it the case now that, I mean, it would be very nice if it turns out that this sigma algebra is the completion of that sigma algebra, because then we could finally somehow relate these two by some theory, you know? And it is. So that's 152, I think, in the book. But basically what we need to do then is to take any Lebesgue measurable set E, we need to lock it inside between two sets which are Borel measurable. But we don't know what the Borel measurable sets look like, right? No, but there is a way of constructing very simple Borel measurable sets that has this property. So now we come to the idea of regularity, but let me introduce it first in the context here of just Lebesgue measure. So I think this is proposition 141 or something. So the Lebesgue measure of some set E in the Lebesgue sigma algebra is equal to the supremum of the Lebesgue measure of compact sets, where the compact sets are subsets of E. Okay. And we also have that the Lebesgue measure of any Lebesgue measurable set is equal to the infimum of any open set that's bigger than E, so this goes the other way around. U, so lambda D of U open. Okay, maybe I should have some set notations here as well. The point is, so compact sets and open sets, they are in the Borel sigma algebra, right? But knowing this proposition here, 141, whose proof I'm also omitting, just go and read it for yourselves. It's not that complicated, you have to do some things. But right, so armed with this, we can easily construct sets A and B like this. Yeah, so how would we do? Well, here's a supremum, which means that if I go a little bit below this value, I can find a compact set such that this measure is bigger than, so if we look at, let's take it like this, take sets A n such that the Lebesgue measure of A n is bigger than or equal to the Lebesgue measure of E minus 1 over m. Yeah? And then you look at the infinite union of these Kns. Now, obviously, this set is in the Borel sigma algebra, because we're allowed to take in countable unions. And obviously, by this proposition 125 or whatever we always use, we have that the Lebesgue measure of this guy. Well, actually, 125 to apply it, we need increasing sets. But if you look at this and call that something else, these are still compact sets, and they are increasing, and then take a limit on that, yada yada. So it's easy to see that lambda of A is equal to lambda of E, right? And this is the key point. I stopped using this D now, so just to make notation a bit simpler. And we can play the same game with the open sets, right? So I pick open sets which are less than or equal to lambda of E plus 1 over n. I play the same game here. I give a set B, and now lambda of B by proposition 126 then will have same measure as E, at least if E has a finite measure, and otherwise it's true also by trivial. So this way of constructing sets by taking, so if you have a collection of sets like all the compact ones, if you then take all the possible unions, this is not too complicated, right? You can clearly get complicated sets. You can get all open sets like this, for example. That's easy to see. You can get all closed sets by doing this process, yeah? How do you say, if you have a closed set, you just consider the open set of all points whose distance to the closed set is less than 1 over m, do an infinite intersection, and you get back to a closed set. So, but the collection of all sets that arise like this is called, okay, so this will need some arrows here. So collection of all possible sets like this is called G delta, D. And this is called F sigma, right? So, yeah. So this is good news, right? Because now we were always saying that, okay, so organizing my thoughts here. So first of all, this and these are Borel sets. E is stuck, well, it has the same measure, right? Lambda is complete on the Lebesgue sigma algebra. So this kind of says that we've always been saying like, oh, these sigma algebras are so big, we don't know how the sets look like. Yeah, but you can always lock whatever complicated set you have in between a set like this and a set like that. And since the difference is of measure 0, it kind of doesn't matter. You can just replace it with this guy or that guy for 99.9% of all purposes. And now suddenly life just became a lot simpler. So then you can start asking yourself, well, okay, so these F sigmas and the G deltas, how do they really look like? And that is investigated also at the end of 1.1, I think we skipped that. Yeah, so this is around 1.1.6, where they, for example, prove this, what I said, that every closed set can arise like, is a G delta, and every open set is a F sigma. And then they start talking about, you can iterate this process, right? So now if we look at all sets of this type, we can start, if we then take infinite intersections again, we just land in the same space. You can't, because you already have countable intersections here, and countable, all becomes countable. So you don't get anything new. But if we start taking unions instead, then you could call them G delta sigma, you get something bigger. And then you could take infinite intersections of all sets of that type and go on like this. Do you ever then get the Borel sigma algebra? As long as you stick to finite many combinations, you always get a bigger class every time, and you never get the Borel sigma algebra. But if you do this process an infinite amount of times, so delta sigma, delta sigma, delta sigma, delta sigma, you will get your Borel sigma algebra. So there is a constructive way of actually doing that. And that is proved in this chapter. I always tell you it's useless. Maybe it's not that useless. Chapter 8 on Polish spaces. So in Polish spaces, just some metrizable topological spaces, basically. And then so if you have a more abstract topology or topological spaces, then the topology can have certain properties. It doesn't need to be a metric. But as long as you have a topology, you can always talk about the Borel sigma algebra. The Borel sigma algebra is the smallest sigma algebra. It's the one generated by all open sets. Yeah, so for that, yeah, you can be in any X that has a topology. So that they define in chapter 7. And in chapter 8, they go ahead and look at Polish spaces. So this is when the sigma algebra, the topology is generated by a metric, and I forgot, possibly some other assumptions. And there in some exercises in 8.2, they actually prove in that general the Borel sigma algebra you get from repeating this process infinitely many times. So that is 8.2 exercise 7. So by iterating so I stick to the RDs, that's what we're discussing here. And the same with the G deltas, I just pick one of them. Here, okay. that works as well. Okay, so we have a way of constructing the Borel sigma algebra. And let me, I think I said this already, but let me write it out on the blackboard, that this is the completion of the Borel sigma algebra. So very nice results. Okay, so again, I'm not doing proofs now because I just want to give you the overview here. If you start doing proofs, then you just lose sight of, you don't see the forest because of all the trees. But I mean, all the proofs here are kind of simple. And I remember when I read it, as a student, it was hard because of just too much information. Here, there are two propositions, 154 and 155, about inner and outer measures. I don't think they are very interesting. I would skip maybe those. So, okay. So 151 and 1 up to 153, this is about completion of measures and with a focus on proving this, that what I wrote here. So that's very nice stuff. End of that story. Now, next story, regularity. So we used here in this construction, this property, yeah? And there is nothing here. I mean, this is clearly a very nice property to have. And most likely many spaces will, many measures will not have this property, right? So it's nice to have some terminology for it. So truth with modification, this, if I just switch here, I write mu instead of lambda d everywhere, then this becomes the definition of regularity. So measures which have this property, we're going to call them regular. Now, what I said is true as long as you stick to measures in RD. That's proposition 156, I believe. Any finite measure on RD has this property. Right, and this is a good definition of regularity as long as you stay in RD. It's equivalent with the technical definition. But then again, in chapter 7 and 8, they go into more abstract spaces where, Hausdorff topology. And there, apparently, this definition needs some modification to apply. And the modification is very strange. So basically, what we're going to require is that this lower property here, it doesn't need to hold for all sets E, but just for the open ones. Whereas this one is going to hold everywhere. So really why that is needed is beyond me to explain you now. I would be happy with the simpler definition, but we have to follow the book, so that's what I'm going to do. Okay, so definition. There's some third silly condition as well. Forget. So each compact subset should have finite measures. We allow infinite measures, but the compact subsets should be a finite measure. Okay, I don't write that on the blackboard, but so here are the two key ones. So if these two hold, then mu is called regular. And then there's a proposition. If mu is regular on RD, then this is 1, this is 2. Right, so we have to be maybe a bit careful about sigma algebras here. Mu is called regular Well, I mean, if mu works on the Borel sigma algebra, this is, I guess, understood here, then it's called regular if it satisfies this. Well, it can be any sigma algebra. Okay, here, if mu works on the Borel sets, my point is if something is regular with the Borel sigma algebra but exists on the bigger sigma algebra, then it is regular there as well because of this completeness. At least on the completion of the Borel sigma algebra, it is again regular. That's easy to see by what I said above. So we don't really need to worry about this. But let's stick here with just Borel sigma algebra, so we don't get confused. So this should hold for all Borel sets E, and in RD, this will also hold for all Borel sets E. That's how it is. In more abstract spaces, this one is more general than if we stick in E here, that's too restrictive apparently. Okay. Right, and the proof of 156 is no surprise. So basically you look, so despite having done the fancy definition, we're gonna check these 1 and 2 that they hold for.
So what we're gonna prove is that mu of E is equal to the infinimum, mu of U, yada yada, and we're gonna prove that mu of P for any Borel set is equal to the supremum, mu of K, where K is even, okay, K less than or equal to E, and K closed. This is even more general, and then to go from close to compact is not so hard. So E subset P, I get tired of writing this, mu open, right?
So we have these two formulas. As long as we're on RD, this holds when you have a finite measure. And how would we prove that? Well, you just consider that R is one of these typical proofs. So that R be equal to all sets in the Borel sigma algebra with the above property, right? So do open sets have this property? Well, clearly the infimum, I mean, if E is open itself, then you can take U to be equal to E. So then this infimum will be that set, right? And as I said, you can always write an open set as F sigma, right? So union of closed set, which are increasing. So then we get also this property by this 1, 2, 5 proposition we use all the time. So it's very easy to see that the open sets are in here. And now we just need to prove that it's a sigma algebra. And for that, they use some trick. So they play with some epsilon. Okay, but read the details in the book. So that about that. We're done. Next time, differentiation of measures. So that was, that was chapter 1 through 5, and my candy is finished. Good, then I go home and buy more candy on the way. See you next time. Chapter 5, we've already done it, so that we'll plunge into chapter 6, which is super exciting. And we'll finally resolve that, what I said with the derivatives and this super version of fundamental theorem of analysis. Coming to that, we're gonna do change of variables. You do that once in your life properly. And that's very boring. That's also done in chapter 6. And after that, we start with the more exotic or esoteric parts of the book. So thank you for today and see you next time.